Hi everyone. So the plan for today and going into next week is that, well, as you would have read if you read my post on Teams, there won't be a SAC next week. The plan is today we'll start on the new area of study 2 on light and matter, and then I realized that this is a pretty big and important lesson, so you'll do it today, and then next Tuesday you'll basically just be continuing on with work around this topic. So this one's going to run across 2 lessons. It'll be a big video, I imagine, so get comfy, get a snack or something, but after that, if we're back on Wednesday, we do revision, then on Thursday you do the GAT, and then hopefully the Tuesday following that you'll be doing the SAC for our previous area of study, the one that we just finished yesterday, or today is Wednesday where I am. So what we're looking at today is on the photoelectric effect and treating light as a particle. Now, this is something I've talked about before. For a long time, people debated whether light was a particle or a wave. In this area of study, we will consider the behaviors of light that can only be explained if light is treated as a particle. This is in contrast to our last area of study, where we treated light as a wave, capable of doing wave-like things like diffraction and interference. And some behaviors of light can only be explained using the wave model, and some can only be explained using the particle model. Because of this, we say that light displays wave-particle duality. It behaves both as a particle and as a wave. So in this area of study, we're looking at the particle-like things about light, things that you can only explain using the particle model. The photoelectric effect, today's concept, is going to be a big part of that. Now, when we treat light as a particle, we assume there are small packets of light which we call photons, and each photon is going to have an energy equal to E, its energy, equal to H times F. So if we treat light as a small chunk of energy, or but as a particle in this case, it's got energy because we're treating it as a particle, and we're going to calculate its energy using this equation. So F is the frequency of light, the energy depends on the frequency, H is a number that we call Planck's constant. It's going to be 6.63 times 10 to the negative 34 joule seconds, and it's a number that we're going to see quite a bit in this area of study. We're going to use it quite a lot. It's just a number that we use when we do a whole heap of these calculations. Now, when we deal with photons, the energies are often very small, tiny energies associated with light. We can use a different energy unit than the joule to describe energies. Instead of using the joule, we're going to use what's called the electron volt, shown by a little e and a big V. Now, to give you an idea of what an electron volt actually is, if you've got one electron and it's accelerated through a voltage of 1 volt, it gains 1 electron volt worth of energy. So if you've got 2 plates, there's a volt of voltage between them. The electron goes from one plate to another through that 1 volt. It ends up with 1 electron volt of energy. That's why it's called the electron volt. It's an electron going through 1 volt, gets an electron volt worth of energy. We convert between electron volts and joules using this, that 1 electron volt on its own is 1.6 times 10 to the negative 19 joules. We've got how to convert from one to the other. So if we've got joules and we want to get electron volts, we divide by 1.6 times 10 to the negative 19. If we want to convert electron volts to joules, we multiply by that factor instead. So just remember that. And an easy way to remember whether it's multiply or divide is that electron volts are smaller units, so the numbers end up being much bigger. So you should, I've got an example there, make it a bit more straightforward. Now, another thing to keep in mind is Planck's constant. I said that was 6.63 times 10 to the negative 34 joule seconds. You can also write an electron volt second version. Now and then we make use of the electron volt second version instead, because it suits the situation that we've got a bit better than the joule second version. We take that joule second version, we divide it by 1.6 times 10 to the negative 19, converting the joules to electron volts, and we get at 4.14 times 10 to the negative 15 electron volts seconds. So that's one we'll be seeing as well. They're 2 different versions of the same thing, both are Planck's constant. One's just joule seconds, one's electron volts seconds, and the situation that you've got, as we'll see later, determines which one you would use. So an example would be a photon has a frequency of 5 times 10 to the 14 hertz. Find the energy of the photon A in joules, B in electron volts. So for question A, we want its energy in joules. We take our equation for the energy of a photon, E equals HF. We've got Planck's constant as 6.63 times 10 to the negative 34 joule seconds. times the frequency of 5 times 10 to the 14 hertz, and we get out 3.1315 times 10 to the negative 19 joules. So a very small number, a very small energy. Now for part B, I could take my answer from part A, and I could divide that by 1.6 times 10 to the negative 19. That would turn my joules answer into electron volts, and that would get me out my answer straight away. So if I've already done A, the quick way to get B done would just be divide by that factor, and that turns your energy into electron volts. Alternatively, I could do the calculation from scratch using the electron volts second version of Planck constant. Do that to get you a sense of how this will work. So I've got the same equation as before, E equals HF. This time what I do is I plug in not the joule seconds version, but the electron volt seconds version of Planck's constant, the 4.14 negative 15. Frequency is going to be the same, and when I do that calculation, what I get out is an answer that's got electron volts as its unit. So 2-ish electron volts. You can see that that number there is a lot more easy to handle, understand than part A's answer, which was 10 to the negative 19, a very tiny number, and it's hard to really conceptualize how small that is. When you get an electron volts answer, it's going to be like 2, 5. It's like a normal-ish number. It can be very small, but still, this is what we normally deal with. We've got electron volts. We expect the numbers to be more ordinary, and so if you do a conversion from from joules into electron volts, you expect the number normally to be pretty standard, not like super high or super low, although on rare occasions it might be. That's kind of a check you can use to see whether you've done the conversion right. Is my number like a bit more ordinary than my joules version? Now, just a bit of a side thing, with light, we know from previous lesson that we've got the equation C equals F times lambda. The speed of light is equal to its frequency times its wavelength. We rearrange that to get that second equation. Frequency is speed of light divided by wavelength. We take our equation equals HF and we replace the value of F with the value from the top line, and we get out this equation which tells us the energy of a photon if we know its wavelength rather than its frequency. And that's what I'm going to use in the second example. It says a photon has a wavelength of 500 nanometers. What is the energy of the photon in joules? So we take that equation for the energy of a photon, and we just plug in the numbers that we've got. We've got our Planck's constant, which is 6.63 times 10 to the negative 34. Tells me I want the answer in joules, so I use the joules second version of Planck's constant, and that will get my answer in joules, times 3 times 10 to the 8, the speed of light, divided by the wavelength, 500 nanometers, so 500 times 10 to the negative 9. Put all that into a calculator, make sure it's going okay with all the timesing and dividing, and you get out about 4 times 10 to the negative 19 joules. So I could either do it this way, or I could just convert the wavelength into frequency using the wave equation from up above, and then use E equals HF instead. I've just chosen to show you how this equation works. If you do it the other way, you'll get the same answer, so it doesn't matter too much. Now, that's background. That's light as a photon, having a wavelength, having an energy, all that stuff. Now we're going to be getting into the photoelectric effect. So one phenomenon that couldn't be explained using the wave model of light was the photoelectric effect. When light was shone on a piece of metal in a circuit, the metal would sometimes emit electrons and allow current to flow, but sometimes it would not, depending on the wavelength of light. The electrons released by the metal due to the light are called photoelectrons, and the current is called the photocurrent. So we're going to talk about photoelectrons. Don't mix them up with photons, the light from earlier. Photoelectrons are just electrons that are emitted because light gives them energy and makes them jump out of a metal and move through a circuit normally. So you can see that in the picture there. You've got a circuit. You can basically ignore the voltage source and the voltmeter and the ammeter and the circuit, and focus on a little bit down the bottom. You can see you've got a cesium metal cathode, and then you've got an anode which is separated by it physically, and you've got light coming in as shown by those orange arrows. And what happens is that electrons jump out of the cathode and move across the gap to get to the anode, which allows current to flow around that circuit. If there was no light there, the electrons wouldn't be able to jump out of the cathode and go to the anode, so you wouldn't get any current. So try and visualize it like that. That's the scenario we're going to be dealing with. You got a cathode, you got an anode. The light causes electrons to jump out and go to the anode from the cathode. That's really all that the photoelectric effect is going to be, where it's situated. Now, we get into the nitty gritty, which is that it was found that if the frequency of the light shone onto that cathode was at or above a particular value, electrons would be emitted. If the frequency was below this value, electrons would not be emitted. So this cutoff value above which electrons are emitted and below which they are not emitted, we call that the threshold frequency and give that the symbol F0. And what I've got here, and this is like a good faith thing, there's two links as part of this PowerPoint that I can't show you because I can't include them. I couldn't figure out how as part of this presentation. So I recommend actually just pausing the video here, going to that link and playing around with what you can see there, because I think the two links in this are kind of great, and if you give them a bit of a play around with, you get a good intuitive feel for what's going on here. If you just listen to me talk, it doesn't come across as well. So please just pause the video, go to that link, play around with it, change some stuff, see what it looks like, and you will benefit from that. Maybe you did that just then, maybe you didn't, but moving on regardless. If the frequency is above the threshold frequency, increasing the intensity of the light will change how much current is flowing. If the frequency is below the threshold frequency, no matter how high the intensity gets, there's still no current. So you think of it as you've got a threshold frequency. If the light has a frequency above that, you get a current flowing, and if you increase the amount of light, the intensity of the light, you get more current. If it's below the threshold frequency, no matter how intense the light is, there's no current flowing. So there's the cutoff point, the threshold frequency that we use to figure out whether we get the current, a photocurrent, or whether we do not. Now, I said before that we can only explain the photoelectric effect using the particle model of light. If light was a wave, then as more light shone on the metal, more energy should be given to it, and eventually enough energy should be there for electrons to be emitted. So if light's a wave, like waves do, they just keep coming in. If the light keeps shining in, the more energy should come in, and eventually the electrons should get enough energy from those waves that they jump out, and so we should see that going on. That's not the case. If the frequency is below the threshold frequency, electrons are never emitted no matter how long the light shone on the metal. So we expect that if light was a wave, a certain thing would happen, and that thing doesn't happen, but we can explain it using the particle model instead. This suggests the particle model of light, where what you've got is a single photon coming in on its own, hitting the electron in the middle, hitting the metal, interacting with just one electron, and it either gives that electron enough energy to jump out of the metal or not giving it enough energy to do so. So it's not an accumulation of energy like waves coming in one after the other. It's just a simple one photon comes in, interacts with one electron, gives it energy. That electron's either got enough energy to jump out of the metal or it doesn't. And this is how the particle model of light explains the photoelectric effect. Another thing that light as a wave would predict is that what you would expect is that there's a brief delay between the light hitting the metal and the electrons being released while the energy accumulated. So what you would expect to see if light was a wave was that the energy would come in and take a bit of time to accumulate in the electron, and then the electron would jump out after a while. What you see in practice is there's no delay. It's just the light comes in and then the electron jumps out straight away, or nothing happens if you're below the threshold frequency. And again, that supports the idea of light behaving like a particle. It's doing something that you'd expect light to do if it was a particle, and that can't be explained if light behaves as a wave. Now, here's the same picture as before, except what I've changed is that it's hard for me to see my video things over the picture. I've got the cathode's negative, there's a negative sign above it, and I've got the anode positive. So that's what it says in the dot point there, and that's what's shown on the picture there. All the signs are a bit small. So now we've got that voltage source in that picture. We're going to make use of it now. We can set the voltage so that the anode is positive and the electron releasing cathode is negative. And what you would expect is that the electrons leave the negative cathode. They are going to be pulled towards the positive anode because they are repelled by the negative cathode and pulled towards the positive anode. They're negatively charged, so that's what you'd expect. And so they're going to gain speed as they're pulled towards the anode. This goes back to year 11. When we talk about current, we're talking about how many electrons are passing a certain point each second. and there are still the same number of electrons being released, so the current remains the same. So in this situation, if you increase the voltage, make the anode more positive and the cathode more negative, the electrons would be moving faster, but the current measured isn't going to change because you've still got the same number of electrons going from cathode to anode. They're going faster, but you've still got the same number of them. Here's another link, another really good one for you to play around with, and please pause the video now and just give it a go, because I don't know what to tell you, it's worthwhile and it helps you out. So if the voltage is reversed, there's now a repulsive force pulling the electrons back towards the cathode, and you can see that in the picture there. I've now got the cathode positive, the anode negative, so we've got the reverse of what was going on the last slide. If the voltage is strong enough that none of the electrons can reach the anode, then no current will flow through the circuit. So reverse of the situation before, rather than being pulled towards the anode, they're getting pushed away from it back towards the cathode, and if you get the voltage strong enough, none of them will be able to cross that gap and get to the anode, in which case you've got no electrons reaching the other side and you don't have any current flowing. The electrons basically just start out, as you'd see in that link if you went to it, the electrons start out the cathode, they move towards the anode before they eventually move back to the cathode that they started at. None of them have enough energy to get to the other side when the voltage is strong enough. Now, side note that you're going to need to know, the electrons in the metal are bound to it, they're stuck in it, and they need some energy to get ejected from that metal. Some of the electrons are less tightly bound than the others and need less energy to be ejected. These can be called the least tightly bound electrons. So this is going to be a concept that we see going forward. You've got the electrons in the metal, some are stuck in it really tight and would need heaps of energy to be ejected. Some are less tightly stuck and don't need quite as much energy. The ones that would need the least energy to jump out of the metal, we're going to consider those particularly. We call those the least tightly bound electrons, so keep that in mind going forward because you will be seeing that term. And it ties in with the stuff I was covering on this slide. Next slide. So when an electron leaves the metal, it has kinetic energy, it's moving, with the least tightly bound electrons having the most energy. The least tightly bound ones need the least energy to leave the metal, so when they have left, they're the ones that have the most residual kinetic energy left over, so they're going to be moving the fastest. As the negative voltage is increased, less and less electrons can reach the other side, reach the anode, because there's more voltage pushing back against them. Eventually, even the least tightly bound electrons are stopped by the voltage and no longer reach the anode. The voltage at which this happens is called the stopping voltage. So what's happening is that you increase the voltage and less electrons can get to the other side. The slower ones get turned back towards the cathode. Eventually you get to a point with the voltage where the voltage is so strong that none of the electrons can get to the anode, at which point you call that the stopping voltage. You got no current, and so that's why it's called stopping voltage. It's the voltage at which the electrons stop getting to the other side. That picture kind of illustrates that. What we've got is the voltage along the bottom and the current along the top, and you've got those two lines. So if I look at line I1, the bottom one, you can see that above 0 volts, you've basically got a constant current. So when you've got a positive current, a positive voltage, the current doesn't really change. As you get into the negatives though, what happens is the line starts going downwards towards 0. That's because the voltage is pushing back some of the electrons. You've got less electrons moving across the gap, less current flowing. Eventually, if you get to that value of minus V naught, that's going to be your stopping voltage. When you get to that point, you've got a current of 0 because none of the electrons are able to cross the gap, so there's no current flowing. If you increase the intensity, go from line I1 up to line I2, for a positive voltage, you've got more electrons flowing across the gap, so you've got a higher current. But if you change the voltage and you go into the negative volts, then you'll, regardless of the intensity of the light, you still have the same stopping voltage. So those two lines show light with the same frequency. It says down the bottom, frequency 1 equals frequency 2. So the stopping voltage is going to depend just on that frequency. Doesn't matter how many electrons there are. If you've got one frequency of light, you can figure out what the stopping voltage is going to be. So far there have been two main factors when we describe the photoelectric effect. there's going to be the frequency of the photons, their energy coming in, and the external voltage that's applied. The other main factor that we're going to look at that determines what's going on with a certain photoelectric effect setup is going to be the metal that's used as the cathode. Now, some metals have less tightly bound electrons than others. This is quantified using what we call the work function phi. I think it is. Could have checked beforehand, I guess. But work function of a metal states the minimum energy needed to release an electron from the metal. And an example would be if sodium has a work function of 2.36 electron volts, then a photon needs to have at least 2.36 electron volts for it to release an electron from sodium. So if a photon has less than that energy, it'll come in, hit the metal, the sodium, and no electrons will jump out. If it's got energy above that, then electrons will jump out. The least tightly bound ones are going to jump out from that metal. That's what it means for the work function to have that particular value. Okay, so I just took a break, and I recommend you take a break, to refresh your memories. But now that we've covered all that, what we're going to do as the last part of this lesson is link all those things together. So we want to link the frequency of the photons, the voltage that's being applied, and the work function of the metal. That's what this last chunk of the lesson is going to be on. So the work function is the minimum energy needed for an electron to be emitted. Looked at that already. We can write it as the work function is Planck's constant times the threshold frequency. So this is basically saying that an electron needs that much energy, the energy of the incoming threshold frequency photon, in order to be emitted. If there's more energy from the photon than that, the electron will be emitted from the metal. If there's less energy than that, because you're below the threshold frequency, then the electron won't be emitted and you won't get any current. So example is sodium has a work function of 2.36 electron volts, whereas the threshold frequency for sodium, we just grabbed that equation from before, the threshold frequency is, the work function is 2.36 electron volts, and so we use that equation up in the second dot point with the numbers put in. The value for Planck's constant in this case is the electron volts seconds version of it, because I've got my energy in electron volts, so I use the electron volts second version of Planck's constant. And if I do that, when I calculate my frequency, it'll come out in hertz like I want it to. So my threshold frequency is just the work function 2.36 electron volts divided by the Planck's constant version that's in electron volts seconds, gets me 5.7 times 10 to the 14 hertz. So a reminder of how this works. If the frequency is above that value, 5.7 times 10 to the 14 hertz, you get electrons jumping out of the sodium metal. If the frequency is below that value, you get nothing. Now for the next slide, we're going to talk about the work done by the stopping voltage, or by the voltage that's being applied, I guess, as shown in that equation there. So we got big symbol W for the work done, the energy given by the voltage or taken away by it. So that's shown by the big W. Don't go confusing the work done by the voltage with the work function, which is about the metal and how strongly the electrons are bound to it. So two very similar things, work and work function. Got to keep them in order so that things don't go getting muddled. So the work done by the voltage, the energy given by the voltage to the electrons, if you've got one configuration, or taken away, which is what we're going to be looking at mostly, is W equals the charge of the electron times the voltage between the anode and the cathode. If the voltage is the stopping voltage, if you're at that exact voltage, then you got that equation W equals QV, with V replaced by the stopping voltage. This is the energy taken away from the electrons, which start with the most energy, the least tightly bound electrons, going back to those particular electrons. It can be deduced that this is equal to the amount of kinetic energy that the least tightly bound electrons started with, which we're going to call EK max. So to go back over that point, you've got electrons. The ones that are least tightly bound will leave and get to the other side. Eventually, if you apply the right negative voltage, the electrons will basically stop reaching the other side. They'll almost get there, but then they'll turn back, as you would have seen in one of those links if you'd use those. And from that, we can figure out that the amount of energy that gets taken away from the electrons has to be equal to the amount of kinetic energy that they started out with. That's the only way that they can basically just only stop reaching the other side, if the energy taken away is equal to the energy they started with. So we're going to play around with that. So the maximum kinetic energy an electron can have is equal to the energy of the photon that gives it its energy, subtract the work function, the energy required for the electron to leave the metal. So what you can see there is that, actually I've probably got another thing, it's hard to tell what I've got. We've got that equation, I should have had that up before. So this is the equation that kind of links a lot of concepts together. The maximum kinetic energy of the emitted electrons is equal to Planck's constant times the frequency of the light shining on the metal, take away the work function of the metal, the amount of energy electrons would need to leave it. You got that little picture there, it shows the stopping voltage for purple light, which has high energy, and red light, which has low energy. Purple light's high frequency, red light's low frequency, and you can see that the purple light has a bigger stopping voltage. There needs to be a bigger voltage applied between the anode and the cathode to stop the electrons emitted by the purple light than the red light, because the purple light photons will give the electrons more energy. The electrons leaving that metal will have more energy. It will take a higher voltage to stop them getting to the other side because they have more energy. The red ones, the red light has less energy, gives the electrons less energy. It takes less voltage to stop the electrons emitted by the red light. So that's just what that graph is showing there. Now, putting it all together into an example, you've got light with a frequency of 5 times 10 to the 14 hertz incident on a metal which has a work function of 1.5 electron volts. Question A, where's the maximum kinetic energy of the emitted electrons in electron volts? B, what is the stopping voltage? So to figure out A, just use the equation from the last slide. The maximum kinetic energy of the emitted electrons is equal to HF, take away the work function. I'm going to use the electron volts version of Planck's constant because I want my answer in electron volts and my work function was in electron volts, so it makes sense to do things that way. 4.14 times 10 to the negative 15, my Planck's constant, times the frequency, 5 times 10 to the 14 hertz, take away the work function, 1.5 electron volts, gets me 0.57 electron volts. So that's the most energy the electrons are going to have when they leave the cathode. That's how much kinetic energy they'll be trying to shoot across to the anode with. Now, question B, where's the stopping voltage? This can be answered the easy way or the hard way. I'll show you just how it works rather than trying to talk it up. So we want to calculate the stopping voltage, and we're going to use this equation to do that. Remember that W is the work done by the voltage, the electric field between the two plates. Q is the charge of the electron flying across. So the amount of work that needs to be done by the voltage in order to stop the electrons getting to the other side is equal to the amount of energy that they started out with. From the previous example, we said that the maximum kinetic energy of the electrons was 0.57 electron volts, so that's how much energy has to be gotten rid of by the voltage. We take that energy, 0.57 electron volts, we convert that into joules by timesing it by 1.6 times 10 to the negative 19, so that left side of the equal sign, that's the energy of the electrons that has to be taken away in joules. That equals the charge of the electron, 1.6 times 10 to the negative 19 times V naught. So that's all that stuff plugged into the equation, and if you solve that equation, what you get out is V naught equals 0.57 electron volts. And hey, what do you know? If you already know EK max in electron volts, the stopping voltage has the exact same value as this. Just remember to put the units as volts. So I found that the maximum kinetic energy in part A was 0.57 electron volts. That tells me the stopping voltage is going to be 0.57 volts. So I could skip that calculation if I want to and just say, well, EK max is going to be equal to the stopping voltage when they're both in electron volts, and use that to figure out my answer a bit quicker. That's the easy way if you want a question like this. Last slide, almost at the half-hour mark. You've got a graph there. That graph shows two lines. Each one follows the equation EK max equals HF minus theta. It's expressing them as a graph. So on the vertical, you've got the maximum kinetic energy of the photoelectrons. It's in joules, and it's been converted sort of into electron volts in this case. Nice that, nice. And along the horizontal, you've got the frequency times 10 to the 14 hertz. And you've got the line for if light is shone on potassium, and also if it's shone on magnesium. Now, I already said that. What you've got here is, if you look at that top equation, EK max equals HF minus theta, that's of the same basic form as Y equals mx plus c. You've got your Y is EK max, you've got your X is F, and you've got the other bits there too. You can look at it and see. What that tells us is that if we've got those two lines on our graph, we can determine the gradient of the lines, and that would get us Planck's constant, and the y-intercept would be the work function. So the two lines have the same gradient because the gradient of both the potassium line and the magnesium line should be Planck's constant, so they should be parallel lines with the same gradient. They have different y-intercepts as they represent different metals with different work functions. So you can see that for potassium, it's going to cross at about minus 3.6 or something down at the bottom. So that's going to be the work function for potassium would be 3.6. For magnesium, it's going to cross that vertical line at about minus 6, so it tells you that magnesium's got a work function of about minus 6 electron volts. Another thing on here, I don't know if I've got another dot point about this, who knows, I don't want to click because this is the last slide, is that if you look at the potassium line, there's a solid part and a dotted part. Basically, the solid part is above the threshold frequency and the dotted line is below the threshold frequency when you wouldn't get any electrons emitted. Where it crosses the horizontal axis is going to be the threshold frequency. So if you look at potassium, for example, you can see that it's crossing the horizontal line at about maybe 5.2 times 10 to the 14 hertz. That tells you that for potassium, the threshold frequency for that metal would be 5.2 times 10 to the 14 hertz. For magnesium, it's crossing the horizontal axis about maybe 8.7 times 10 to the 14 hertz. That tells you that magnesium's threshold frequency is 8.7 times 10 to the 14 hertz. So this graph like these are a very common way of showing the photoelectric effect. The different parts for a certain metal are that the gradient would be the Planck's constant, and the y-intercept is your work function for the metal, and the horizontal intercept is your threshold frequency. So from a graph like this, you're getting all kinds of properties about your setup for your photoelectric effect. Which is why I just said last dot point. Glad I didn't, could have talked over that anyway. So this should be the last slide. I'll be embarrassed if it's not. But the idea is that we're starting on chapter 10 today, so you want to do the questions from 10.1 of your textbook and the checkpoints questions as well. Please try and get those done. Like I said, this is a long lesson, so we want to spread it over this lesson and the next one on Tuesday. So if you need to, don't, try and do as much work as you can. That's the ideal, but try and make sure that next lesson you're doing a bit on this as well. Coming back to this video if you need to. The lesson plan, the questions are all up available on Compass under the resources section. So make sure you're downloading that so you can follow along exactly what you're going to need to do. All the solutions for the checkpoints and the textbook questions or work solutions are on Compass, so use those if you're stuck, and make sure you're just emailing me or sending me a Teams chat or whatever if you need some help with any of it. But that's really all that there is from me. Hope to see you tomorrow. We'll see.